Sorry, it's an Oreo. Gotta chew some more. Oops. Hi, everyone. So, this is assignment. Wow, we're getting up there in sequences and series. This would be assignment 72. Okay, assignment 72. We're talking about sigma notation today. We're going to continue our discussion about using these rules for sequences. Why don't we start with this? We've got -1, 1, 3, 5, 7, and so on. Okay, can you write me a rule for this? I don't know how you do it without having. So if I plug in a 5, I should get 7. 5 times 2, that's 10. Better subtract 3. Well, let's see if that works. And if I plug in a 3, I should get a 3. 2 times 3 is 6, minus 3 is 3. Nice. How about if I plug in a 1, I should get -1. 2 times 1 is 2, minus 3. Yeah, there's my rule. Okay. So that's a sub n. Now, that was working with sequences. Today, we're going to talk about series. And a series is the sum of a sequence. I know, right? It has this completely different meaning than I thought. I thought I could have used sequences and series as synonyms for each other. But no. This is the sequence, and the series, -1 plus 1 plus 3 plus 5 plus 7. That's the series. The series is the sum of that sequence. Okay. So, yeah, sum. Do you remember the notation that says sum? It uses sigma notation, sigma for sum. Sure. If we were looking at this situation here, I would think of it as sigma, or the sum of the things that come out of this, right? These are the things that come out of this from n equals 1, from this one to that one. So this means -1 plus 1 plus 3 plus 5 plus 7, and so we get 15. So when we see this notation, we should have some way of getting us to 15. Okay, well, I want to say that there's an expectation. When you see this number is fairly small, or when these numbers are fairly close together, then I can just, take the 1 and plug it in, take the 2 and plug it in, and the 3 and plug it in, and the 4 and plug it in, and the 5 and plug it in. And I'm only plugging in the numbers from 1 to 5 inclusive. And that'll give me these outputs, which I could then add up. That's one way to do these problems. And I think in many of the problems you'll see, you can get away. In fact, not only get away with, but the expectation is that you'll be plugging things in like I just did. So if we have k equals 0 to 5 of k plus 1, k minus 1, well, I'm going to plug in a 0, 0, 0, I'm going to have -1. Then after I plugged in 0, I'm going to plug in all the other whole number values until I get to 5. 5 will be the last one to plug in. So now I'm plugging in 1. 1 plus 1 is 2. 1 minus 1 is 0. So I'm adding 0. I plugged in 1. I plugged in 2. In fact, oh goodness, why don't we just do this? 0, 1, 2, 3, 4, 5. These are k values, and a sub k, I plugged in a 0, I got negative 1. I plugged in a 1, 1 minus 1 is 0, so 0 times stuff is 0. I plug in a 2. 2 minus 1 is 1, 2 plus 1 is 3, 1 times 3 is 3. I plug in a 3, 3 minus 1 is 2, 3 plus 1 is 4, 4 times 2 is 8. I plug in a 4. 4 minus 1 is 3, 4 plus 1 is 5, 3 times 5, 15. And if I plug in a 5, 5 minus 1 is 4, 5 plus 1 is 6, 4 times 6 is 24. So this sum is the sum of these values. So 3 plus 8 plus 15 plus 24. Okay, so what do we get? 39, 47, 50, 49. So this equals 49. Good, and all by hand. No extra formulas needed. I just had to sort of grunt through plugging in all the values from 0 through 5. Okay, how about something like this? Sigma k equals 1 to 6 of 2k minus 3. So I plug in a 1. 1 times 2 is 2. 2 minus 3 is negative 1. I plug in a 2. 2 times 2 is 4. 4 minus 3 is 1. I plug in a 3. 6 minus 3 is 3. I plug in a 4. 8 minus 3 is 5. And I plug in a 5. 10, 7. And I plug in a 6. 12 minus 3 is 9. Right? And we can see that sequence from our last video. These are all going up by 2 because that's a times 2. And what's my sum equal to here? 16 and 8 is 24. So this sigma is 24. All right. Even if I have something like k equals 21 to 23 of k plus 1 over 2. Well, I'm going to start by plugging in a 21. 21 plus 1 is 22. And then I'm going to plug in the next value, which would be 22. 22 plus 22 plus 1 is 23 over 2. And then finally, I'm going to plug in a 23. So plus 23 times 23 plus 1 is 24 over 2. All right, I mean, I'd certainly love to tidy this up, but I don't see a lot of obvious opportunities for that. I guess I've got 11 times 21 plus 23 plus 23 times 12. So that's 44 times 11 plus 23 times 12. 23 times 12 plus 44 times 11, and I get 760. Okay. Yep, so if these numbers are small, or if there's not a lot of values between, I'm going to plug in a 21, a 22, a 23, I'm all done. I might as well just, plug those numbers in. Okay. So, what about partial sums? Partial sum. So, for example, if I see I equals 1 to infinity, yeah, I'm sorry, I got other classes. I can't write out an infinite number of terms in this sequence that I would then add together. So instead, I want to think about a partial sum. And so they're actually going to give me a number in these problems. Like for this one, we're asked to find the fourth partial sum. And what that means is instead of using this infinity here, I'm going to plug in a 4. So I've got I values and a sub I. If I plug in a 1, because that's where I'm starting, and then a 2 and a 3, and the last one is 4 because I want the fourth partial sum. So I'm plugging in values for I. 1/2 to the 1 is 1/2 times 5, 5/2. And if I plug in a 2, 1/2 squared is 1/4 times 5, I get 5/4. If I plug in a 3, 1/2 to the third is 1/8 times 5, I get 5/8. Yep, and this is going to be 1/2 to the fourth, or 1/16 times 5 is 5/16. I would make a common denominator, so I'm going to need 8/8 times 5/2, plus I'm going to need 2/2, no, 4/4. 4/4 times 5/4, plus 2/2 times 5/8, plus 5/16. So this is going to be 40/16, plus 20/16, plus 10/16, plus 5/16. 60, 70, 75/16 is my answer. The fourth partial sum of this infinite series is 75/16. Okay? So what if, instead of that sigma, we were looking at this sigma? N equals 1 to infinity of 8 negative 1/4 to the n. And please find the third partial sum. Okay, pause the video, give it a try. Hey, welcome back everyone. So, third partial sum, well, that means I'm going to be plugging in for n, 1, 2, and 3, because we're stopping at third partial sum. If this was seventh partial sum, 1, 2, 3, 4, 5, 6, 7, starting at 1, ending in 7. But we only have the third partial sum. So, a sub n, if I plug a 1 in here, well, that's negative 1/4 to the 1, or negative 1/4 times 8 is negative 2. Now, if I plug in a 2 here, negative 1/4 times negative 1/4 is 1/16 times 8. That's going to give me 1/2. And if I plug in a 3 here, that's negative times negative times negative. 1/4 to the third is 1/64. But I'm multiplying by 8. So I end up with negative 1/8. Remember though, ours is a sigma. Ours is a sum. So I need to add up negative 2 plus 1/2 minus 1/8. And if I make a common denominator here, negative 16/8 plus 4/8 minus 1/8. That's negative 17 plus 4, negative 13/8. Is my third partial sum. Okay? Now that's not to say we won't look at infinite sums. I mean, we really won't do a lot with infinite sums. But in Calc 2, yeah, you're going to have infinite sums. So let's look at some infinite sums. They look remarkably similar. But we won't have them for any and everything. In fact, I've only got 2 problems here. K plus 1 to 1/10 to the k. These are very similar, and I'd like to take a look at how I'm supposed to come to an understanding of what this sum is, this infinite sum. Like I'm plugging in, starting with 1, 2, 3, 4, 5, 6, 7. Don't stop till you get to infinity. And so there must be some way for us to understand this. Yes. And it turns out that that 7, that constant, can just go out front. And I can figure out this infinite sum and then multiply by 7. Or this infinite sum and then multiply by 2. And isn't that interesting? I'm going with 1/10 raised to my term number. So this is the same in both cases. Well, let's see what's happening here. If I plug in a 1, what am I going to get? I'm going to get 1/10 to the 1 is 1/10. And if I plug in a 2, I get 1 over 100. And if I plug in a 3, I get 1 over 1,000. I think we know where this is going. 10,000. Good. And I don't see where this is getting me, but this is one of those cases where I actually prefer decimals to fractions. If I write 1/10 as a decimal, I have 0.1, and 1/100th, 0.01, and 1/1000th, 0.001, and 1/10,000th, 0.0001. And remember, this is saying add them all up. Add them up. Adding them up. And so what am I going to get? 0.11111. And this is going to go on forever. So we know this as 0.1 repeating. And you might say, well, 0.1 repeating times 7. Well, I actually want to take this a little further. Many of you in middle school saw what I'm about to do next and have forgotten it. Some of you haven't actually ever seen it. It's this. 0.9 repeating equals 1. Now, many of you remember in middle school saying, well, 0.9 repeating looks like that. And that is not 1. Right? It's just 0.9 repeating forever. Well, yeah, so it turns out on that sort of list of things that you were not as clear about as you might have been, if I have 0.9 repeating, let's call that x. Yeah? And remember, I'm saying that 0.9 repeating is actually not close to, but actually 1. Not close to 1 is 1. Okay? 0.99999 and keep going. That turns out to be exactly 1. And I'm going to show you how over here. Let's say that x is 0.9 repeating. And then let's multiply both sides of this equation by 10. Okay? On the left, I'll have 10 times x, or 10x. And on the right, when I take this and multiply by 10, that's just going to move the decimal over 1. So I'm going to have 9.9 repeating. Okay? You buy that? Is that good? All right. Now, subtract. On the left-hand side, 10x minus 1x is 9x. On the right-hand side, 0.9 repeating, 0.9 repeating, and I'm subtracting. And I have 9. And if I divide both sides by 9, I get x equals 1. And therefore, 0.9 repeating is 1. So, tell me about this? Well, I know that if I take 0.9 repeating and divide it by 9, well, that's going to be 0.1 repeating, isn't it? And what did we say 0.9 repeating was? 0.9 repeating was 1, and so I end up with 1/9. So this thing here, this 1/10 thing, remember what we had? We had 1/10, 1/100th, 1/1000th, and so on. And then we turn that into decimals. Oops. 0.01, 0.001. And then we added these things, and we know that we were going to get 0.111, etc., repeating. Going to go on forever. Okay, well, I know that 0.1 repeating is 1/9 because 0.9 repeating is 1. So if I divide both sides of this equation by 9, I get 0.1 repeating is 1/9, not 1/2, 1/9. Cool. So this is 1/9 times 2. This is 1/9 times 7. So this one's going to be 7/9, this one's going to be 2/9, and that's all I need. Okay. Yeah, that's interesting, isn't it? I don't plan on doing that to you, but you know, Mr. Paz, he's very comfortable with the content in Calc 2, and he might want to actually do some more than I just did. Okay, so now I want to look at something like this. I want to look at a situation. I want to look at a situation where we actually have a whole bunch of stuff to deal with. Or am I just deriving? No, I've got stuff. Okay. So what if I have k equals 1 to 40 of 3k squared plus 5k minus 4? Well, I'm sorry, Mr. U, but I love you, but there's no freaking way I'm plugging in all the numbers from 1 to 40 in here and adding them up. And I agree. And that's why instead of plugging in the numbers 1 to 40 and then adding them all up, that's why first I'd like to investigate some sigma shortcuts. Okay? And our first sigma shortcut is going to be the sum from k equals 1 to n of a constant. The sum of a constant. So for example, k equals 1 to 5 of 3. Well, I don't have a little k here, so there's no place to plug in the numbers. So instead, this is what happens. I plug in my k values of 1, 2, 3, 4, 5. Except there's nowhere to plug them. That's okay. This thing just keeps saying, I'm 3, I'm 3, I'm 3. And then we add these up. And so I have 5 times 3, I get 15. And over here, what if I had k equals 1 to 7 of 4? Well, okay, 1, 2, 3, 4, 5, 6, 7. Oh, but look, there's no place to plug these k values in. This is just 4, 4, 4, 4, 4, 4, 4. Huh, 1, 2, 3, 4, 5, 6, 7. And I get 28. So this is 28. Now, I'd like you to tell me what's the shortcut rule for the sum of a constant. How is it that I could just look at this and come up with that? How is it that I could just look at this and come up with that without having to do all this legwork in here? Yeah? I think you see it. I think most of you see it. Constant times n. K equals 1 to c. I'm sorry, 1 to n of c is going to be n times c. If I just multiply that times that, I get that. If I multiply that times that, I get that. All I have to do is multiply these together to get that. Okay, there's my first sigma shortcut, the sum of a constant. Okay, well, I'd like to explore 2 more of these with you. The next one is k equals 1 to n of k. Now, I know you're saying, like, but that's the same as you just did. No, because look, these are the same. And so I really do have a place to plug in all those numbers, 1, 2, 3, 4, etc., etc. So let's actually do some. K equals 1 to 4 of k. Well, I plug in a 1, I plug in a 2, I plug in a 3, and I stop after I plug in 4. And I get 7, 10. And what happens if I have k equals 1 to 5 of k? Well, again, 1 plus 2 plus 3 plus 4 plus 10 plus 5. And I get 15. And if I do k equals 1 to 3 of k, it's just going to be 1 plus 2 plus 3. And that's 6. So I'm looking and I'm seeing something very interesting. Plug in these k values. And the sum of those k values is, I guess I'll start with the 3. 3, 4, 5. Actually, we could do that. That's good. Because if that was a 1, if that was a 2, I'd have 2 plus 1, or 3. And when we had 3, 6, and 4 gave us 10, and 5 gave us 15. Okay? Now, what do you notice? I agree. These don't go up by the same amount each time. But that doesn't mean I can't write a rule for them. No, really. Check this out. It's really, yeah, this is really an interesting thing. So normally what we would try and do is we would try and relate the factors times 5 back to these term numbers. Well, here I see the term number is 2, and this is 1 less than that, and this is 1 more than that. Well, do I have this situation here where one of the factors is 1 less than that, and the other one is 1 more than that? No, that didn't work. Well, here I see 1 more than, but I see 2 less than. And here I see 2 less than, but 3 more than. So I don't see any pattern in these factors. Right, I don't either. However, and this is a number theory thing, if I multiply those sums by 2, and then I factor, do you have a way of relating the term number to these factors? That's the same as the way you could relate this term number to these factors. Do you see it? Do you see that they're the same, they're the same, they're the same, they're the same? And so one of our factors is going to be the same as that number. Now what about these other numbers? What's the relationship here to here, here to here, here to here, here to here? Well, this is 1 more than that, and this is 1 more than that, and this is 1 more than that, and this is 1 more than that. So this has to be 1 more than that. Okay. So that's close. If I take my n value, I'm sorry, my k value of 3. 3 plus 1 is 4. 3 times 4 is 12. But I'm supposed to get 6. And if I plug in my 4, 4 times 4 plus 1 is 5. 4 times 5 is 20, but I'm supposed to get 10. So I'm getting these numbers, but I need these numbers. So divide by 2. Remember when we doubled? Well, when we're all done building our rule, we have to undo that doubling, which is why we're dividing by 2. So what's our rule? N plus 1 over 2. Now, I understand. Mr. Kukla, I'm lost. What the hell are you talking about? Yeah, no problem. So I don't expect you to derive these rules. If this were honors trig, sure, we could derive some rules on a test. But for us, this is what I need you to know, so that when you see k equals 1 to 20 of k, you know that you're going to take that n value and plug it into our formula. 20 times 20 plus 1 over 2. And that's going to be 10 times 21, or 210. And I tell you, that's a whole lot faster than taking the numbers 1 to 20 and adding them all up. That's what that represents. It's the sum of the numbers from 1 to 20, because this is the counting thing. This is k equals 1, k equals 2, k equals 3, k equals 4, and just adding them all up. And this is perhaps a little faster. Nice. And so if this is 30, well, I'm just going to plug in 30 for each of those n's. And so I'm going to have 15 times 31. 15 times 31, and I get 465. 465. Well, that's cool. I mean, that's like, wow, okay, I can do that. So, one more. The sum k equals 1 to n, not of a constant, not of k, but of k squared. Okay? And, you know, if we start generating some values, k equals 1 to 4, I'm looking at 1 plus 4 plus 9 plus 16. And if I'm talking about k equals 1 to 6, and I'm looking at 1 plus 4 plus 9 plus 16 plus 25 plus 36. Okay, I'm adding up all the squares from 1 to 6. Cool. Well, it turns out there's a pattern here as well. It's a different pattern than the k to the first pattern. This one, and you know, again, because we're honors, I would make you find the pattern. The pattern here, actually, doubling didn't work and tripling didn't work. I had to actually multiply all these values by 6 in order to find a pattern in their factors. So rather than force you down that horrible road, or that long and interesting road, depending on your perspective, that's my shortcut. And so I'm going to say you should probably memorize your 3 sigma shortcuts. Why? Well, I'll explain in just a moment. K equals 1 to k n was n plus 1. Don't forget the over 2. And the very first one we looked at, k equals 1 to n of some constant, that was just n times the constant. Good? Okay. So now what are we going to do with these things? Well, I want to do this. K equals 1 to 30 of 3k squared plus 7k plus 2. Yeah, I know, there's a lot going on there. So the first thing I'm going to do is I'm going to break this down into 3 smaller sigmas. K equals 1 to 30 of 3k squared plus k equals 1 to 30 of 7k plus k equals 1 to 30 of 2. How does that help? Well, don't I know the sum of a constant is simply that constant times this upper value of 30? So I know this is going to be 2 times 30, or 60. And here, I mentioned before, these constants, we can just factor them out. And if we had more time, we'd go through a discovery process where we understand why and yes, that we can do that. So now look what I've got here. I've got the sum of k from 1 to 30. What was the shortcut for k equals 1 to n of k? It was n plus 1 over 2. That's my n. So that's my n. So I'm going to have 30 times 30 plus 1 all over 2, but don't lose this, times 7. And over here we have the sum of k squared. And remember the sum of k squared? Sum k equals 1 to n of k squared was n plus 1. So many people want this to be n plus 2, but it's not. And I would actually make a note to myself to remember what it really is before I take a quiz or test on this. So this is k equals 1 to n of k squared. We're going to have n. We're going to have n plus 1. We're going to have 2n plus 1 all over 6. Yes, n plus 1, not n plus 2. 2n plus 1. So when I plug in my 30 here and here and here, what am I going to have? Well, I'm going to have 30 times 31 30 times 2 is 60 plus 1 is 61. All over 2 is 6. And then don't forget we have this coefficient out in front. Okay, so what I'm saying is that this sigma can be broken into these 3 sigmas, and then I can use the appropriate shortcut for each one. Now, I think before I pull out my calculator, I'm going to do a little tidying. 6 and 3, 2, and 2, and 15. So 15 times 31 times 6. Oh, I guess I could have just canceled. Oh, that's 61, not 6. No, I couldn't have canceled. Plus 7 times 15 times 31 plus 30 times 2, or 60. So we've got 15 times 31 times 61 plus 7 times 15 times 31 plus 60. And I get 31680. There's no way you're going to get me to plug in the numbers 1 to 30 there and then add them all up. Sigma shortcuts, yeah, definitely my friend. So, shall I do one more and then you can do one more? That'll be 18. Okay, so K equals 19 to 40 of 3k squared plus 7k plus 2. Okay, so this is a little different. In the last problem, we went k equals 1 to 40. Well, 30. And, we split this up into 3, and I think that's fabulous. Except, remember those sigma shortcuts that we made? Yeah, those sigma shortcuts require that be 1. Well, it's not 1 here, Mr. Kukla. Right, which means, as written, I can't use my shortcuts yet. And that's a problem. At least I think it's a problem. I really don't want to plug in 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Oh, I'm too bored already to even get to 40. Plug all those values in, add up all those outputs. No, there's got to be an easier way. So let's imagine this. Let's imagine the sum of k equals 1 to 40. Okay? Same 3k squared plus 7k plus 2. But really, I'm just thinking about this part. This is going to represent adding up all the values from 1 to 40. Now, this one says, I don't really want to add them all up. I just want the 19 through 40th all added up. So, here's what I'm going to do. I'm going to take the sum from k equals 1 to 40, and I'm going to subtract from it this. Well, what's that? That's k equals 1 to, be careful here, this is probably going to be a highlighting and arrows and stars moment, 18. Why 18? Well, remember, we're only using numbers like 1, 2, 3, 4, etc. So no decimals, no fractions in there to worry about with these countings. And I want the 19th. So I want to get rid of everything before the 19th. So that means go up to 18. This number is always one less than that number. When I have to split these things up into 2 different sigmas, because this does not start with 1, and my shortcuts only work if I start with 1. Yeah, only work if I start with 1. So I'm having to create a situation where I get to start with 1. One of my sigmas goes from 1 all the way out to whatever that is. But that's overcounting. I need to get rid of the sum of these first 18 terms. And so I'm going to go from 1 to 18. And so when I look at this sigma, not starting at 1, but starting at 19, First thing I'm doing is saying, all right, well, that's k equals 1 to 40 of 3k squared plus 7k plus 2 minus k equals 1 to 18 of 3k squared plus 7k plus 2. Okay? Whenever this does not start at 1, I'm going to have to split into 2 sigmas. And this is always 1 more than that. This has got to be 1 less than that. Okay? If I made this 19, I'd be counting off the first 19 of them. I need 19 through 40 here. So I don't put 19 here, I put 18 here. Okay? And then how do we do this? Well, this, we're going to say that's the same as 3 sigma k equals 1 to 40 k squared plus 7 sigma k equals 1 to 40 of k plus k equals 1 to 40 of 2. And now I'm going to use the shortcuts for each of those, right? Remember your k squared shortcut, remember your k shortcut, remember your shortcut for a constant. So what's that going to look like? Well, the shortcut for k squared is n plus 1, 2n plus 1, plus 2n plus 1. There we go, 81. All over 6 plus 7 times 40 times 41 all over 2. That's a 7. And plus 80, right? Because that times that. But hold on, we still have this one to do. So this one, I'm going to go up to 18 with each of them. And so when I use those shortcuts, I'm going to say, okay, well, that's going to be 3 times 18 times 19 times 2n plus 1, 37 over 6, plus, I'm plugging in 18, 18 times 19 over 2. Hey, don't lose that coefficient. And then finally, I have plus 18 times 2. Now, I've seen lots of students over the years get this far and not get the answer right. And that would be terribly, terribly frustrating. And the reason why most of them don't get this right is they forget that they're subtracting all of this stuff. Many people just say, I'm just subtracting this one. No. I'm subtracting this one and this one and this one. In fact, maybe I want to add up all of those and add up all of those and then do the subtraction last. All right, so why don't you type into your calculator. I'll type in my calculator, and we'll see what we get. I'm actually going to simplify a little first. Not necessarily for any good reason. That's the number 7. Good. And over here, and here. Okay, so I've got okay. This is 72240. And now over here, 9 times 19 times 37 plus 6 times 9 times 10, 630 plus 36. Okay, and this is 6993. So 72,240 minus 6,993. I get the sum here should be 65247. All right. There you go. Guess what? It's your turn. Here's yours. Okay. K equals 10 to 80 of 2k squared minus 3k plus 5. Okay. Will you please evaluate that sigma? I'm going to have to put, why do you do that? Mm. One to what? Remember, this is one less than that. Okay, so break this down. 2k squared, 1k minus 3k, 1k plus 1 to 80 of 5 minus 2 times k equals 1 to 9 minus 3, 1 to 9 plus 1 to 9 of 5. Okay, now I'm going to use my shortcuts. 2 times k squared was n plus 1, 2n plus 1 over 6. Okay, minus 3 times n times 1 over 2 plus 5, the constant times n. Okay, minus, and now I've got to repeat over here. Here I'm going to run out of space, so let's see what happens. So this is n plus 1, 2n plus 1, don't forget that times 2, all over 6, minus 3 times 9 times 10 over 2, plus 9 times 5. Okay, so I'm subtracting this minus this plus that. That's a little awkward. So I'm going to take a 2 out of there and a 3 out of there. That's going to be 40. That's 2 and 9 and 10 and 19. So I take that 2, I take a 3, and over here I can do a 5. Okay, so what am I looking at? I'm looking at 80 times 27 times 161 minus 3 times 40 times 81 plus 5 times 80 minus, and we've got 30 times 19. Now, this is minus a minus. I'm actually going to be plus 45 times 3. 45 times 3. I feel like I should be able to do that in my head. 12, 13, 135. Okay? And then minus this positive minus 45. All right, let's see what that comes out to be. We've got 80 times 27 times 161 minus 3 times 40 times 81 plus 5 times 80 minus 30 times 19 plus 135 minus 45. And I come up with 337960. Wow. And so rather than add up by plugging in a 10, 11, a 12, a 13, a 14, all the way up to 80, and then adding up all those values, I can use my sigma properties to break this into a couple of sigmas, and then I can use my shortcuts after I've broken this down further. Wow. Yeah, I would put something like that on a test, for sure. Do you want one more, or are you feeling like you can do that now? We'll do one more. But really, see if you can do this before I reveal my answer. Okay? How about k equals k equals 11 to 20, 3k squared plus 5k minus 4. Okay? Please find that sum. Yeah, they do take a little while, don't they? I'm still sure it's much faster than plugging in all the numbers from 11 to 20 and trying to figure those out and then add up all of those. Yeah, not going to do that. I am going to say, ooh, this isn't 1. So the very first thing I have to do is split this up into k equals 1 to 20 minus k equals 1 to, not 11, 1 less than. Okay, so I'm looking at there. If only I had more Greek in me. K equals 1 to 20 of 3k squared plus 5k minus 4. And then I'm going to subtract k equals 1 to 10 of 3k squared plus 5k minus 4. Cool. Now this gets split up into 3 different sigmas. 3k squared from 1 to 20 plus 5k from 1 to 20 minus, we could just do that, right? Minus all of these split up. 3k squared from 1 to 10 plus 5k from 1 to 10 minus 40. So let's use our k squared shortcut and our k shortcut now. K squared was n plus 1, 2n plus 1. 3 times 20 times 21 times 41 over 6. This is the other thing that students forget. Like they want to make this n plus 2 instead of 2n plus 1. And they want to make that a 2. It's not. It's a 6. This one, always a 6. Plus 5 times 20 times 21 over 2 minus 80 minus 3 times 10, 11, 21 over 6 plus 5 times 10 times 11 over 2, and don't forget that minus 40. Okay, and this is what we want to use our calculator for. I'm actually going to tidy this up a little bit. Okay, so that's going to turn out to be 10. Yeah, I took the 2 and the 3 for the 6. So 10 to 10 times 41 plus 50 times 21. That's a minus. So 50 times 21 minus 80 minus 55 times 21 minus times positive is negative 25 times 11. 5 times 5 times 11, and minus a minus is plus 40. So I get 210 times 41 plus 50 times 21 minus 80 minus 55 times 21 minus 25 times 11 plus 40. And I end up with 8190. So the sigma from 11 to 20 is going to have that sum. Okay, so know your sigma shortcuts. Yeah, know your sigma shortcuts. That's cool and easy. That's it for this video. Please ask questions. Please let us know if you need help with anything. And the next video is all about arithmetic sequences. Those are the sequences that go up by, a common difference each time. It'll be easy. Trust you. Trust me. Okay, have a great day, everyone.